Chem 2005. Today we will talk about 1,2-azoles, and then we will finish the lesson talking about a little bit about oxazolidinones and pyrazolones. What are 1,2-azoles? Well, 1,2-azoles are basically this type of structures. Okay, where X could be NH, oxygen or sulfur. These are basically the structure of a 1,2-azole. It's basically very similar to the 1,3-azole, but now the two heteroatoms are one next to the other. We're going to start checking if it's aromatic. 2, 4, 6 electrons, cyclic, planar, all atoms sp2. That means that this is aromatic. Okay, and in terms of basicity, the 1,2-azoles are slightly less basic, than 1,3-azoles. Why? Because next to the atom where we have the pair of electrons in the sp2 is another electronegative atom that decreases the basicity of the nitrogen atom. Okay? What more? Well, how we can synthesize 1,2-azoles? Well, if we check the structure of a 1,2-azole, okay, this is the structure. The first thing that we can do is, for example, we put 2 nitrogens in order to do it easily. What we can do is break. This is an enamine, okay? And we know that the enamine is coming from the reaction of an amine plus a ketone or an aldehyde. Okay? Next step, this can come. We only need to break this bond. That means that what we have is the addition of one free decarbonyl compound plus hydrogen if we want to get the azole with 2 nitrogens. The 1,2-azole with 2 nitrogens. Okay, what is the mechanism? Well, we have the hydrogen that will react with 1,3. For example, we are always in acid media. That means that we protonate the carbonyl, and then the nitrogen of the hydrogen will attack here, forming the enamine. Next step, we protonate the other carbonyl compound, and what we get is that amine, the other amine is forming again an imine, we form this compound, and then simply tautomerization and this imine or this imine we can form with enamine to form the final compound. Okay? What happens if instead of hydrazine we use a substitute hydrazine? For example, we use here a phenyl. Okay? This nitrogen has a hydrogen and has a phenyl. The reaction will be the same. The nitrogen will attack the carbonyl group. Okay? Which carbonyl group? Because now we have two carbonyl groups, and this will determine which is the reactivity. With amine, why is attacking this amine? Because this amine is the most accessible. Okay? Will attack the more electron poor carbonyl group. What means this? Okay, it means I mean that we have this type of compound. Okay. We have this. We have this one free deketo compound, okay, and we are attacking, for example, with this hydrazine. Which carbonyl will be attacked by the hydrazine? Well, we can have these two options, but the nitrogen will attack this carbonyl compound, this ketone only, because this is more electron withdrawing. That means it's attracting more electrons because we have a nitro here. That means that this will be more electron poor. And the rest of the mechanism will be exactly the same. Okay? In this case, obviously, the tautomerization has to be with this. And what we will get is this compound. Okay? But check, if we have a substitute hydrazine, what we need to do is basically, first we know that the most reactive nitrogen will be the nitrogen that is free, that is NH2. Okay, and then we have to choose which carbonyl will be the more electronegative, the more electron poor, sorry. This carbonyl or this carbonyl. What we need to do is to check the substituents. For example, if it's an aromatic ring, which aromatic ring will be more electron poor? This aromatic ring is more electron poor because we have a nitro. This aromatic ring will be more electron rich because we have a donating group, electrodonating group like the methoxide, and then the nitrogen will attack the most electron poor carbonyl, and following exactly the same mechanism than before. If, for example, we want to form instead of a diazole with two nitrogens with one nitrogen and one oxygen, we treat our one free decarbonyl compound with hydroxylamine. Which is the most nucleophilic atom? Will be the nitrogen, okay, because it's less electronegative than not the oxygen. That means that this will attack where? To the more electron poor carbonyl, for example, this. And now what we will have is the formation of the imine. we protonate the other carbonyl group and then the wedge will attack. And the only difference is that now, when we have this compound, we will have this intermediate. Again, what we will do is to move the proton. This proton that is over the oxygen, we will put it in the wedge in order to make a very good leaving group. Then the leaving group is departing. And what we get the carbocation that will do the elimination to form the aromatic compound. Okay? And this is the way to form, the most common way to form 1,2-azoles. Remember, what is important of this synthesis is, first of all, identify which of the heteroatoms is the most nucleophile. In the case of hydrazine, it will be the nitrogen that is less substituted, that is free, is NH2. In the case of hydroxylamine, will be the nitrogen. Okay? And then simply we have to decide in which of the carbonyls will take place the reaction. And will take place because it's a nucleophilic attack with the more electron poor carbonyl. And how we identify the more electron poor carbonyl, we have to check the different substituents that we have. Okay? There are a way to synthesize this type of compounds, and basically is from, we have this compound, okay, we have this alphabet unsaturated compound, unlike before, we attack with, for example, hydrazine or substituted hydrazine or even, okay. If we do this, what will happen? The first step will be the addition of this compound to the carbonyl group, to the beta position, doing a Michael addition. I do it with this, but you can do it with any of these compounds. Okay, it will be the same, following the rules that we did before. What we get is we get the Michael addition, then, sorry, this is protonated in order to activate. And then the next step is the wedge is attacking the carbonyl compound. generate this intermediate. Again, we move this proton from this oxygen to the hydroxyl group in order to make this hydroxyl group a better leaving group. And then the water is departing. What we get is this carbocation that, don't forget to put the hydrogens in the nitrogen, okay? We do the elimination of the proton to generate this compound that then can be oxidized by CAN to generate the final aromatic compound. Okay, it's very similar to the other, but the only is like first we start with a Michael addition. Okay, then the second atom, the second heteroatom is attacking the carbonyl group. We do the elimination, and we get a partially hydrogenated 1,2-azole that oxidation with CAN will give us the final compound. Okay? Basically, this is a two synthesis that you need to know of 1,2-diazoles. Remember that in the case of 1,3 carbonyl compounds, it's crucial to determine which is the most active carbonyl group, that means which is the more electron poor carbonyl group. Okay, and finally we will talk about the synthesis of pyrazolones and oxazolones. Pyrazolone is this compound. And oxazolones is this compound. These two compounds are very important because they are precursors for the synthesis of alpha amino acids or beta amino acids. Okay, we will start with the pyrazolones, how we can synthesize it. Okay. Basically, in order to synthesize pyrazolones, we can do this. We can break this bond, and then this is coming. This is coming basically from the reaction of an ester with this compound. Okay? Next step, we can break this bond. This is amine. That means that this will come from how we do the forward synthesis. Basically, we have this keto ester. How we can synthesize keto ester? Remember, Claisen reaction, the condensation of of two esters. Okay? Here we have this compound, and then we add the hydrazine. These reactions always are in acid, always. That means that first we protonate the oxygen of the carbonyl, and then what is happening is that this reacts with the carbonyl, forming the imine. Okay, and then the pair of electrons of the amine will attack the ester, addition, elimination to form the final pidazolone. Okay? Why this compound is important? Because basically this is the reactivity of this compound. If we treat this with a base, and we don't need a very strong base, basically, we can have this anion that is stabilized by resonance, and if we add, for example, our methyl iodide, what we will do is the addition in this position. Okay? Then, for example, we can break this and reduce in several steps, and we get this beta amino acid. Okay?